A machine that was supposed to die nearly 50 years ago is still whispering back to Earth from the edge of the solar system. Voyager crossed a boundary no human being has ever seen, and what it detected out there shattered decades of scientific certainty about the shape, size, and behavior of the space surrounding our sun. The farther it traveled, the stranger the universe became. Some of its discoveries forced scientists to redraw the map of our cosmic neighborhood completely. And today we explore it. Let's go. Voyager 1 is transmitting right now. 22 watts. That is the power it is using to send its signal across space back to Earth. 22 watts less than the light bulb inside your refrigerator. And yet, that whisper of electricity is crossing 23 billion kilometers of absolute darkness, carrying data from a place no human-made object had ever reached before. Let that land for a second. Not 23 million, not 2,300 million, 23 billion kilometers. If you laid every highway ever built on Earth end to end, you would still need to do that roughly 45,000 times just to match that distance. And at the other end of that unfathomable stretch of nothing, a spacecraft the size of a small car is alive, transmitting, still doing science. This is not a metaphor. This is happening right now, today, as you watch this. But here is where it gets truly strange. Voyager 1 was never supposed to be here, not even close. When it launched on September the 5th, 1977, the mission was designed for 4 years. 4 years, 2 planets, Jupiter and Saturn, a handful of flybys, some photographs, some data, and then it would drift off into irrelevance. NASA engineers gave it a job, a timeline, and a budget. Nobody drew a plan that went further than Saturn. Nobody needed to. The technology alone should have guaranteed obsolescence within a decade. The computer processor on board operates at roughly 240,000 times less processing power than the basic pocket calculator sitting in a dollar store checkout line today. The memory storage, all of it, would not hold a single low-resolution photograph by modern standards. And yet, 47 years later, it is still out there, still functioning, still sending back information from a place that rewrote everything we thought we understood about the boundaries of our solar system. Think about what that means in human terms. The engineers who built Voyager 1, the ones who stayed up at night running calculations, who argued over circuit boards and antenna angles and power budgets, many of them have already lived full lives and passed away. The world has changed beyond recognition since 1977. 8 American presidents have come and gone. The internet was invented, expanded, and became inseparable from daily life. The Soviet Union rose and collapsed, and through all of it, silently and without fanfare, this machine kept going, kept moving, kept watching. Now here is something that genuinely stops people cold when they hear it for the first time. If you sent a message to Voyager 1 right now, a radio signal traveling at the speed of light, the fastest anything can move in the known universe, that signal would take over 21 hours just to reach the spacecraft. And then the reply would take another 21 hours to come back. You would be waiting 43 hours for a round-trip communication? That is longer than most transatlantic and transpacific flights combined. Longer than most people sleep across 2 full nights just for a single exchange of information with a machine we launched into space almost half a century ago. The Deep Space Network, the system of giant dish antennas NASA uses to stay in contact with Voyager, has to point its receivers with extraordinary precision. The signal arriving on Earth is so faint that receiving it requires antennas that are up to 70 meters across, roughly the height of a 20-story building, just to detect a whisper of 22 watts from across the solar system. Engineers describe it as trying to hear a conversation happening on the other side of a continent, in a stadium, during a thunderstorm, with one ear. And this is worth pausing on, because there is something quietly absurd about it. NASA is still communicating with Voyager using antenna infrastructure that was designed and built in the 1970s. The technicians who maintain parts of this system are working with equipment that, in some cases, predates home video players. Gen Z engineers joining the Deep Space Network program today sometimes encounter hardware so old they have to be trained on systems that no longer appear in any modern textbook. Ask one of them what a particular piece of equipment does, and you will occasionally get a look that says, "I have genuinely never seen anything like this outside of a museum." And somehow it works. Voyager 1 is not just surviving out there, it is in interstellar space, beyond the heliopause, beyond the boundary where our sun's influence ends and the true void between the stars begins. It crossed that threshold in August 2012, becoming the first human-made object in history to enter interstellar space, not the edge of the solar system as most people picture it, with Neptune as the last landmark. Far, far beyond that, 121 times farther from the sun than Earth is, a distance so large that the number itself becomes almost meaningless without something to anchor it. Nearly 50 years after launch, it is not just alive, it is somewhere no human object has ever been. And it got there on hardware that most modern devices would not even recognize as a computer. Here is the question worth sitting with for a moment. If a machine this old, this underpowered, this far beyond its original purpose, has already shattered every expectation we had for it, what did it actually find out there? Because that is where this story gets uncomfortable. The discoveries Voyager made at the edge of the solar system did not just add new information to the existing models. They broke the models. The boundary between our solar system and interstellar space turned out to be nothing like what decades of scientific consensus had predicted, not in its location, not in its shape, not in its behavior, and not in what lay beyond it. NASA still uses antenna dishes from the 1970s to hear it, which, honestly, tracks because Voyager itself is still out there, still running on hardware from the same era, proving every year that the universe does not particularly care about your retirement plan. But the fact that Voyager is still alive is not the point. The point is what it found when it got there, and what that means for everything we thought we knew about where our solar system ends and the universe begins. Voyager was born from a coincidence so rare it borders on miraculous. In the late 1960s, a young aerospace engineer named Gary Flandreau was working at NASA's Jet Propulsion Laboratory and noticed something extraordinary buried in orbital calculations. Jupiter, Saturn, Uranus, and Neptune, the four outer gas giants of the solar system, were aligning in a configuration that would make it possible for a single spacecraft to visit all four of them using gravitational assists, swinging from one planet's gravity to the next like a stone skipping across water. This kind of alignment happens once every 175 years. The previous opportunity had been in 1793, when the United States was 4 years old and the most advanced machine in existence was a sailing ship. The next one will not come until 2153. The window was open. It would not stay open long, and NASA had a choice. The full mission, eventually called the Voyager program, launched two spacecraft, Voyager 2 on August the 20th, 1977, followed by Voyager 1 on September the 5th of the same year. Despite the numbering, Voyager 1 launched after Voyager 2, but on a faster trajectory, which is why it overtook its twin and reached the outer planets first. Even in naming conventions, this mission had a way of defying expectation. But here is what most people do not know. The original mission plan was not built around all four planets. It was built around two. Voyager 1 was designed specifically to fly past Jupiter and Saturn, with a particular emphasis on Saturn's moon Titan, which scientists believed correctly, as it turned out, might have a thick atmosphere worth studying up close. That meant Voyager 1's trajectory after Saturn would curve it out of the plane of the solar system entirely, eliminating any chance of visiting Uranus or Neptune. The science was worth the trade-off. Voyager 1 went deep on Saturn and Titan. It got extraordinary data, and then it kept going upward and outward on a path that would eventually take it out of the solar system entirely. Voyager 2 was given more flexibility. Its trajectory was adjusted to thread between all four gas giants, the so-called Grand Tour. It flew past Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989. 12 years of flight, 4 planets, 1 spacecraft. And here is a detail that should genuinely bother anyone interested in planetary science. No spacecraft has visited Uranus or Neptune since not one. Voyager 2 is still the only probe in history to have flown past either of those planets. Everything we know in detail about Uranus and Neptune, their magnetic fields, their ring systems, their moons came from a few hours of data collected during brief flybys by a single spacecraft over 30 years ago. There are entire categories of questions about those planets that remain completely unanswered, not because the questions are too hard, but because no mission has gone back. Now think about the original mission structure. 4 years, 2 planets, photographs and particle measurements, return the data, close the books, move on. That was the assignment. Nobody in the program leadership was drawing up plans for what Voyager might do in year 10, or year 20, or year 47. There were budgets to manage, political cycles to navigate, other missions competing for resources. You plan for what you need, not for what might happen if everything goes improbably right for half a century. There is a comparison here that makes this concrete. Imagine hiring a taxi to take you from Los Angeles to San Francisco, roughly 380 miles, a clear destination, a clear endpoint. You pay, you arrive, job done? Except the driver, instead of turning around, just keeps going, north through Oregon, through Washington, up into Canada, into Alaska. No extra gas stops, no explanation. Just quietly, inexplicably, keeps driving. And 47 years later, the car is still moving, somewhere north of everything, sending back observations about the road conditions in places no map has ever covered. That is Voyager. The mission officially expanded over time. Of course, NASA was not just watching a spacecraft drive into the unknown and shrugging. The Voyager interstellar mission phase formally began in 1989, after Neptune, and redirected the program's focus toward the outer boundary of the solar system and what lay beyond. Scientists on the team understood that the spacecraft might eventually reach the heliopause, the theoretical edge where the sun's influence ends, and that the data gathered there would be unlike anything obtainable any other way. But even that expanded mission was built on assumptions. Assumptions about where the boundary would be, what it would look like, how the spacecraft would behave as it passed through, and what the environment beyond it would contain. Those assumptions were reasonable, carefully constructed, built on decades of physics and observation. Almost all of them turned out to be wrong. Consider this Voyager. One flew past Jupiter, the largest planet in the solar system. A world so massive that more than 1,300 Earths could fit inside it in roughly 2 days. 2 days to cross an encounter with something that enormous, moving at speeds that made the physics feel almost casual. The gravity assist Jupiter provided accelerated Voyager 1 further, slingshotting it outward with energy borrowed from the planet's own orbital momentum. A giant, giving the little spacecraft a running start toward the edge of everything. And then it just kept going. When the planetary mission phase ended and the cameras were powered down to save energy, Voyager 1 was already in territory no human instrument had mapped. The outer solar system, the vast, dark, cold reaches beyond Neptune, was essentially blank space on every chart ever drawn. Scientists had theories about what existed out there. They had mathematical models. They had predictions about where the solar wind would eventually slow down, where the sun's magnetic influence would thin out, where interstellar space would begin. They were confident in those models. They were wrong about almost everything. When the mission's official chapter closed, a group of scientists and engineers made the decision not to power it down. And that is the moment Voyager stopped being a planetary probe and started becoming the most important instrument in the history of space exploration. What it sent back from the edge would force science to rewrite the map from scratch. The heliosphere is the reason you are alive, not in a poetic sense, in a literal, physical sense. Right now, as you exist on this planet, you are inside a magnetic bubble generated by the sun, a vast, invisible shield created by the solar wind, a constant outflow of charged particles streaming from the sun in every direction at speeds between 300 and 800 kilometers per second. This bubble surrounds the entire solar system. It pushes back against the radiation and high-energy particles flooding in from interstellar space, cosmic rays produced by supernova explosions, by neutron stars, by violent events happening in galaxies billions of light years away. Without the heliosphere, those particles would bombard Earth's surface continuously. The atmosphere would erode. The magnetic field protecting surface life would be stripped away over geological timescales. Life, as it exists here, would not. So this is not an abstract scientific concept. It is the shield, the only one we have got. And for a long time, we thought we understood it. For decades, scientists built detailed models of what this shield looked like, and the picture that emerged, the one printed in textbooks, the one displayed in science documentaries, the one that represented careful, hard-won scientific consensus from the 1960s onward, was elegant, logical, satisfying in the way that clean geometry always is. It felt complete in the way that a good theory feels complete, internally consistent, mathematically coherent, and supported by the best available evidence of its time. The standard model described the heliosphere as a teardrop shape, round and blunt on the side facing the direction the solar system moves through the galaxy, called the nose, and stretched into a long tail behind it, trailing away like the tail of a comet. This tail, called the heliotail, was thought to extend for enormous distances in the opposite direction of travel, shaped by the pressure of interstellar space compressing the front face, while the solar wind continued streaming freely outward behind. The whole structure was assumed to be roughly symmetrical on the top and bottom, reasonably stable over time, and well-behaved at its boundaries. A clean, predictable bubble, a shield with a known shape. Scientists were not guessing at this. The model was built on real physics, magnetohydrodynamics, plasma theory, decades of in-situ observation from instruments much closer to the sun. It was the kind of model that earns papers in major journals, gets cited thousands of times by subsequent researchers, and eventually stops being seriously questioned because it has been repeated long enough and widely enough to feel like settled fact rather than working hypothesis. Entire careers were constructed on its assumptions. Funding proposals cited it as established foundation. Graduate students learned it as bedrock, not conjecture. It appeared in every major textbook covering solar physics and space science for the better part of 4 decades. The confidence was total, and that kind of confidence has a long and instructive history of running into reality and losing. Medieval cartographers drew maps of the world with extraordinary care and total conviction. The coastlines of known regions were labeled with precision. Distances were calculated from the best available measurements. Trade routes were marked. Territories were named. Sea monsters were occasionally added to fill in the parts nobody had actually visited. The maps were beautiful objects, detailed, internally consistent, authoritative in their presentation. And in many places they were completely, sometimes catastrophically wrong. Continents were distorted beyond recognition. Oceans were the wrong size. Entire landmasses were invented to satisfy theoretical expectations about what ought to be there. But the cartographers did not know that. They drew what the best available knowledge told them, committed to it fully, and presented it with the certainty of people who had done serious work. When explorers finally reached the places on those maps and found that reality looked nothing like the drawing, the maps had to be pulled apart and redrawn from the ground up. The heliosphere model was the same kind of map, careful, detailed, built in good faith from the best available tools, committed to fully, across 4 decades of scientific literature, and as Voyager's data would eventually prove wrong in ways that nobody had seriously entertained, because the tools needed to test it had not yet existed. Until Voyager. Now, here is a question worth genuinely sitting with for a moment. What could actually distort a magnetic bubble the size of the entire solar system? Think about the scale involved. This structure spans hundreds of astronomical units in every direction. It is driven by the continuous, unrelenting output of a star that has been burning for 4.5 billion years. It contains every planet, every moon, every asteroid, every comet, every speck of dust that orbits our sun. What external force is large enough to push something like that around, to squeeze it on one side, to reshape it from the outside? The answer, it turns out, is everything around it. The interstellar medium, the gas, dust, plasma, and magnetic fields that fill the space between stars is not a neutral, passive, empty environment. It has its own pressure, its own embedded magnetic field with its own orientation, its own direction of flow. Since the solar system is moving through it at roughly 828,000 kilometers per hour as it orbits the center of the Milky Way, the heliosphere is not sitting motionless inside a calm, uniform sea. It is plowing through an ocean that has currents, that has pressure gradients, that has a magnetic structure of its own, and that pushes back. The way that ocean pushes, from which direction, with how much force, with what magnetic alignment relative to the sun's own field, all of it shapes the heliosphere from the outside in ways the old teardrop model had dramatically underestimated. Because the old model had assumed the interstellar medium was far simpler than it actually is. Every variable, the old models either simplified for mathematical convenience, estimated from incomplete data, or quietly set aside as probably negligible, turned out to matter. The interstellar magnetic field orientation mattered. The local pressure of the interstellar medium mattered. The direction and speed of interstellar flow relative to the solar system's motion mattered. None of these were zero. None of them canceled each other out neatly. And when Voyager finally reached the boundary and started measuring the reality directly, not estimating it from a distance, not inferring it from models, but actually being there, the numbers did not match the map. The answer, in short, is everything. And that is exactly the problem. Voyager was heading straight for that boundary, and the data it sent back would erase the map that science had been proud of for 40 years. In 2004, Voyager 1 hit a wall. Not a physical wall space does not work that way, but a boundary, a very real, very measurable transition point where the solar wind, which had been streaming outward from the sun continuously and uninterrupted for the entire duration of Voyager's journey, suddenly could not maintain the speed it had been traveling. The interstellar medium, the gas and plasma filling the space between stars, was pressing inward from outside. And the solar wind, for the first time since leaving the sun, lost the argument. This boundary has a name: the termination shock. It is the region where the solar wind abruptly slows from supersonic speeds to subsonic speeds, compressed and heated by the counterpressure of interstellar space pushing in from the outside. The physics of it can be made vivid with a simple image. Think of a faucet running water directly onto the flat surface of a sink. Where the stream first hits the surface, It moves fast, a tight, rapid jet. But then, just a short distance from the impact point, it fans out and suddenly transitions into a slower, thicker ring of water spreading outward. That transition, that abrupt change from fast to slow, is the shock. The termination shock is that same phenomenon. But the faucet is the sun. The water is the solar wind. The sink surface is the pressure of interstellar space. And the scale is measured in billions of kilometers. Voyager 1 crossed this boundary at 94 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. So 94 astronomical units is 94 times that. Work that out, and you get roughly 14 billion kilometers from the Sun, a distance so large that the light leaving the Sun right now will not reach that point for over 13 hours. Voyager's instruments registered the crossing clearly and unambiguously. Particle counts shifted. Magnetic field readings changed character. And the measured velocity of the solar wind dropped sharply. The data was not ambiguous. Voyager 1 had passed through the termination shock. Then Voyager 2 made the same crossing in 2007. And that is where the first serious, undeniable crack appeared in everything the old models had assumed. Voyager 2 crossed the termination shock at 84 astronomical units from the Sun. Not 94, 84. A difference of 10 full astronomical units between the two spacecraft, and the reason that difference matters so much is what it reveals. Voyager 1 was traveling roughly northward relative to the plane of the solar system. Voyager 2 was heading roughly southward. Same sun, same solar wind source, same outward pressure driving both spacecraft. But in the northward direction, the termination shock sat at 94 astronomical units. In the southward direction, it sat at 84. The boundary was not sitting at the same distance in every direction. It was closer to the Sun on one side than the other. 10 astronomical units of difference. Let that number mean something concrete. 1 astronomical unit is 150 million kilometers the distance from Earth to the Sun. 10 astronomical units is 1.5 billion kilometers. The gap between where Voyager 1 and Voyager 2 each crossed the termination shock, the gap between northward and southward in the same solar system, was 10 times the distance from Earth to the Sun. That is not a rounding error. That is not instrument noise. That is a structural asymmetry in the boundary of the solar system, sitting right there in the data, impossible to explain away. The heliosphere was not the symmetric teardrop the textbooks had drawn. It was being pushed harder on one side than the other. Something in the interstellar environment, pressing against the solar system from outside, was not uniform. The pressure was uneven. The shape was deformed. And the magnitude of that deformation, 1.5 billion kilometers, was far larger than any model had predicted. Picture a soap bubble held between your two open palms. When you hold your hand still and the pressure is equal on every side, the bubble is round. Now press one hand slightly closer to the other. The bubble responds immediately. It bulges outward on the side where you have created less pressure, and it flattens on the side where you are pushing. The termination shock data from Voyager 1 and Voyager 2 was telling scientists exactly this story. The Sun's bubble was being pressed harder from one direction than another. The interstellar medium was not a uniform sea. It had uneven pressure. It had structure. It was pushing on the solar system in ways that distorted the boundary by an amount that dwarfed the entire inner solar system. And this raised a question that nobody in the program could comfortably set aside. If the boundary was this lopsided, if the termination shock alone was off by 10 astronomical units between two directions, what did that say about the models used to predict everything else? The heliosheath beyond the termination shock, the heliopause at the outer edge, the interstellar environment waiting on the other side. All of those predictions had been built on the same foundational assumptions as the symmetric teardrop model. If the foundation was wrong, what did that mean for every layer built on top of it? The short answer, it meant the layers were wrong too, not slightly off, not in need of minor revision, wrong in ways that would take years of analysis and multiple subsequent discoveries to fully understand discoveries that Voyager was still moving toward, 1 billion kilometers at a time, on its way to the true boundary of everything we call home. And if the boundary on the inside was already this distorted, what Voyager was about to find in the churning region beyond it was going to be more violent, more chaotic, and more astonishing than anyone had dared imagine. The heliosheath was supposed to be the quiet part. After the drama of the termination shock, the abrupt slowdown, the compressed plasma, the clear signal of a boundary crossed, scientists expected the region beyond it to behave like a gradual transition, a buffer zone. The solar wind, now slowed to subsonic speeds, would spread outward in a relatively orderly fashion, thinning and cooling as it approached the heliopause, the true outer edge where the sun's influence ends entirely. The models described it as something like the calm water at the base of a waterfall, turbulent at the transition point. Yes, but settling into smoother flow as it spread further out, a region of decreasing energy, decreasing density, decreasing complexity. Simple, manageable, well-behaved. Voyager did not find that. What Voyager's instruments recorded inside the heliosheath was not a gradual, orderly transition. It was a churning, tangled, magnetically chaotic environment that matched none of the predictions in any meaningful way. The magnetic field, instead of lying in smooth, predictable orientations as the models assumed, was twisted and folded back on itself in configurations that took scientists years to fully map and interpret. The solar wind particles, slowed from their supersonic journey, but still carrying enormous energy, were not spreading outward cleanly, they were colliding, reversing direction, piling up in ways that suggested the internal dynamics of the heliosheath were far more violent and far more complex than anyone had modeled. And then came the magnetic bubbles. In 2011, researchers analyzing data from Voyager 1 announced a discovery that genuinely caught the field off guard. The heliosheath was not filled with a smooth magnetic field threading outward from the sun. It was filled with a vast, tangled foam, a structure of magnetic bubbles, each roughly 160 million kilometers across, interlocking and overlapping like soap foam on an enormous scale. 160 million kilometers. For reference, that is slightly larger than the distance from Earth to the Sun. Each individual bubble in this magnetic foam was the size of the entire Earth-Sun gap, and they were packed together throughout the heliosheath in a structure that no previous model had ever suggested, predicted, or even considered as a theoretical possibility. The mechanism producing these bubbles was itself a revelation. As the solar magnetic field is carried outward by the solar wind, it does not maintain a single coherent direction. The sun rotates, and that rotation winds the magnetic field into a spiral, the Parker spiral, named after physicist Eugene Parker, who first described it in 1958. By the time this spiraling field reaches the heliosheath, it has been wound so tightly that it becomes unstable. It breaks apart. It folds back on itself through a process called magnetic reconnection, snapping and reforming into closed loops the bubbles. The result is not a smooth, coherent magnetic environment, but a packed collection of isolated magnetic structures, each one a closed loop containing trapped particles, each one bumping against its neighbors in a region spanning billions of kilometers. The implications went beyond just structure. These magnetic bubbles changed the picture of how particles behave in the heliosheath entirely. Cosmic rays entering from interstellar space, which scientists had assumed would slow down and scatter predictably as they penetrated the heliosheath, were instead finding pathways through the gaps between bubbles, moving in ways that bore no resemblance to the smooth diffusion the models had calculated. high-energy particles from inside the solar system were behaving differently too, bouncing between bubble walls, gaining energy in some regions and losing it in others, creating a particle environment that was patchy, directional, and deeply uneven. Plasma pressure added another layer of disorder. Throughout the heliosheath, the measurements showed pressure fluctuating sharply over relatively short distances, spiking in some regions, dropping in others, with no clean spatial pattern. The old models had assumed this pressure would decrease gradually and monotonically as distance from the sun increased. Instead, it jumped around. It varied by direction. It responded to changes in solar activity in ways that propagated through the heliosheath, like disturbances through a living system, rather than gradients through a static medium. The river analogy makes this vivid. Imagine a great river flowing toward the sea. As it approaches the coast, you expect it to widen, slow, and settle into the broad, calm estuary before meeting the ocean. That is the heliosheath. The models predicted a widening, slowing, calming transition. What Voyager found was the opposite. The river, instead of calming, entered a canyon, rapids, whirlpools, water doubling back on itself, crashing against walls of magnetic foam, throwing spray in every direction with no predictable pattern. The most turbulent, structurally complex region in the entire solar system was not near the sun, where the energy is greatest. It was out at the edge, in the zone everyone had assumed would be the easiest part. There is a particular word that appeared repeatedly in the scientific literature and in NASA communications as Voyager's heliosheath data came in unexpected. The magnetic bubbles were unexpected. The pressure fluctuations were unexpected. The particle behavior was unexpected. The complexity of the magnetic topology was unexpected. In the dry, careful language of peer-reviewed science, unexpected is a neutral term. But in practice, when that word appears this many times in papers describing the same region of space, what it communicates is something closer to, we had no idea. The models we built, the predictions we made, the environment we thought we understood well enough to describe in detail, none of it prepared us for what the instruments actually measured when a spacecraft was physically inside that region for the first time. NASA scientists, to their credit, have always been precise in how they describe these surprises publicly. But read enough of the literature from that period, and a picture emerges clearly. The heliosheath was not a known quantity that Voyager confirmed. It was an unknown that Voyager exposed. Every year that Voyager 1 and Voyager 2 spent inside the heliosheath. Voyager 1 from 2004 to 2012, Voyager 2 from 2007 to 2018 produced data that required existing models to be revised, extended, or in some cases, abandoned entirely. And the heliosheath, as chaotic as it turned out to be, was still the interior, still inside the solar system's boundary, still, technically, home. But all of this, the magnetic foam, the pressure chaos, the particle disorder was just the waiting room. The heliopause was the real door. And what Voyager recorded the moment it stepped through would force physics to start rewriting itself from the first page. In August 2012, Voyager 1 crossed a line that no human-made object had ever crossed before. Not a symbolic line, not an administrative boundary drawn on a chart for convenience. A physical threshold, the heliopause, the outermost edge of the sun's domain, where the solar wind finally runs out of strength entirely and interstellar space begins in full. Beyond this point, the sun's particles no longer dominate. The magnetic environment is no longer shaped by our star. The space beyond the heliopause belongs to the galaxy, not to our solar system. And for the first time in the roughly 300,000 years that anatomically modern humans have existed on this planet, something we built crossed into that territory. The confirmation did not come instantly. It never does with Voyager. The data arrived in pieces, and the scientific team spent months analyzing it before making any public statement. NASA is not an organization that announces historic milestones casually. They needed 3 independent signals, all pointing to the same conclusion simultaneously, before they would say what the numbers were clearly telling them. Those 3 signals arrived together, and they were unambiguous. First, plasma density. Inside the heliosphere, the plasma, the charged gas filling the space around the solar wind, exists at relatively low density, consistent with the outflowing solar wind thinning as it spreads over enormous distances. The moment Voyager 1 crossed the heliopause, the plasma density increased by roughly 40 times. Not gradually, not over millions of kilometers of transition. Sharply. The interstellar medium is denser than the outermost reaches of the solar wind, and Voyager's plasma wave instrument captured that change with stark clarity. 40 times denser, in the span of a boundary. Second, cosmic rays, high-energy particles streaming in from outside the solar system, produced by distant supernovae, by pulsars, by violent astrophysical processes happening light-years away, are partially blocked by the heliosphere. The solar wind and the heliospheric magnetic field deflect a portion of them before they can penetrate deep into the solar system. As Voyager 1 approached and then crossed the heliopause, the count of these galactic cosmic rays surged sharply upward, reaching levels consistent with the unshielded interstellar environment. The partial protection the heliosphere had been providing was gone. Voyager was now fully exposed to the galaxy's ambient radiation field. Third, solar wind particles. The charged particles streaming outward from the sun, the very thing that inflates and defines the heliosphere, dropped to nearly zero. They did not taper off slowly. They essentially vanished. Voyager 1's instruments, which had been detecting solar wind particles for the entire 35 years of its journey, suddenly had almost nothing to measure. The sun's breath had stopped. Everything beyond that boundary was interstellar. 3 signals, all simultaneous, all consistent with one interpretation. Voyager 1 was in interstellar space. The signal carrying this data traveled at the speed of light back toward Earth, and it still took 17 hours to arrive. 17 hours for light itself, the fastest thing in the universe to cross the distance between Voyager and the planet that built it. A full workday, plus an evening. Scientists at the Jet Propulsion Laboratory in Pasadena, California, received data from beyond the solar system after a transit time longer than most people spend awake in a single day. The comparison that comes to mind is the moment a human being first stepped outside Earth's atmosphere. On April the 12th, 1961, Yuri Gagarin crossed from the atmosphere into space, a boundary between the terrestrial and the cosmic that had never been crossed by a living person before. The world reacted with something between awe and vertigo. A new category of human experience had opened, but Gagarin had left the atmosphere, not the solar system. He was still inside the sun's domain, still inside the heliosphere, still in the same cosmic neighborhood his entire species had occupied for its entire existence. What Voyager 1 crossed in August 2012 was a boundary of an entirely different order, not the edge of a planet's atmosphere, the edge of the solar system itself. Now consider the distance involved. The heliopause, where Voyager made this crossing, sits approximately 121 astronomical units from the Sun. 1 astronomical unit, again, is the Earth-Sun distance, roughly 150 million kilometers. 121 times that is just over 18 billion kilometers. If you walked at a normal human pace, without stopping, without sleeping, covering roughly 5 kilometers per hour, you would need approximately 3.4 billion years to cover that distance on foot. For context, Earth itself is only 4.5 billion years old. You would arrive having missed almost the entire history of the planet you started from. And Voyager 1 got there in 35 years. That achievement sits in an unusual place in the human story, too large to fully feel, too real to dismiss. A machine smaller than a compact car, launched on a rocket in the same decade that disco was popular and home computers did not exist, traveled for 35 years through the outer solar system and became the first artifact of human civilization to enter interstellar space. There is no precedent for it. There is no framework in ordinary experience that makes it feel adequately significant. It simply is what it is, the farthest any human-made object has ever gone, doing something no human-made object had ever done. But if you think the heliopause is a fixed line, a wall sitting at 121 astronomical units, holding its position year after year, think again. That boundary is not fixed. It is contracting, expanding, oscillating, and breathing in rhythm with the sun, and what that means for everything inside it is stranger than the crossing itself. The sun is not a constant object. It burns steadily enough from a distance, a fixed point of light, reliable and unchanging in the way that only something 93 million miles away can appear unchanging. But up close, measured over time, the sun is a dynamic and restless system cycling through periods of intense activity and relative calm on a rhythm of approximately 11 years. This cycle, the solar cycle, drives changes in sunspot frequency, in solar flare intensity, in coronal mass ejections, and most relevantly, in the strength and pressure of the solar wind itself. When the sun is at the peak of its activity cycle, called solar maximum, the solar wind blows harder. The pressure it exerts outward, in every direction, increases. And that increased pressure pushes the heliosphere and the heliopause at its outer boundary physically outward, expanding the entire structure by billions of kilometers. When the sun quiets down toward solar minimum, the pressure drops, and the heliopause contracts back inward. The heliopause is not a wall. It is a membrane. It moves. The scale of this movement is not trivial. Estimates based on models and Voyager data suggest the heliopause can shift by several astronomical units over the course of a solar cycle, that is, by several times the Earth-Sun distance, or potentially hundreds of millions of kilometers of displacement over 11 years. The entire outer boundary of the solar system is expanding and contracting in response to the activity of a star sitting at its center, 121 astronomical units away. The heliosphere breathes, and the breath is the sun's. But the sun does not just cycle smoothly, it erupts. Coronal mass ejections, massive bursts of solar plasma and magnetic field, launched from the sun's surface during periods of intense activity, travel outward through the solar system at speeds ranging from several hundred to over 3,000 kilometers per second. These events produce pressure waves, shock waves that propagate outward through the solar wind like ripples from a stone dropped in water. Except the stone is an explosion the size of a continent, and the water extends for billions of kilometers in every direction. By the time these shock waves reach the outer solar system, they have traveled for months or years and spread across an enormous front. They arrive at the termination shock, pass through the heliosheath, and reach the heliopause, and they do not stop there. Voyager 1 recorded this directly. The data collected between 2012 and 2013 captured something remarkable. Two large pressure waves generated by solar events that occurred in 2012 were still propagating through the plasma of interstellar space after crossing the heliopause. The sun had erupted. The shock wave had traveled outward for months, crossed the termination shock, plowed through the heliosheath, crossed the heliopause, and continued moving into interstellar space, where Voyager 1's plasma wave instrument detected the oscillations it produced in the interstellar medium. The instrument essentially heard them. Plasma wave science translates particle oscillations into frequencies that, when rendered audibly, produce sound. The waves Voyager detected were recorded and converted, and NASA released the audio. What it sounds like is an eerie rising tone, a whine building over time as the plasma density around the spacecraft increased in the wake of the shockwave. Scientists described it as the spacecraft listening to the interstellar medium ring like a bell, struck by a hammer swung from 93 million miles away and traveling outward for over a year before it landed the blow. Think about what that means structurally. The sun sneezes, and the shockwave travels for more than a year, crosses the boundary of the solar system, and makes the interstellar medium vibrate in measurable ways. The heliopause is not a sealed container. Events inside it, solar storms, pressure surges, magnetic disturbances propagate through it and continue into the space beyond. The sun's influence does not end at the heliopause. It diminishes beyond it. Yes, but it does not stop. And the reverse is equally true. As the data makes clear, the heliopause flexes inward and outward, not just because of the sun's changing output, but because of changes in the interstellar medium pressing from the outside. If the local interstellar environment shifts, if the pressure of the interstellar gas changes, if the solar system moves through a denser or thinner region of interstellar material as it orbits the galactic center, the heliopause responds. It pushes back out or gets pushed further in. The boundary is a negotiation, happening continuously between two environments, neither of which is static. The image that captures this most honestly is a heartbeat, not a metaphorical one, a structural one. The solar cycle produces a rhythmic variation in the outward pressure of the solar wind, causing the heliopause to expand and contract on an 11-year rhythm. Each pulse pushes the boundary of the solar system outward by hundreds of millions of kilometers, then draws it back. The entire edge of our cosmic home is moving in and out in a slow, enormous rhythm, driven by the nuclear fusion reactions happening at the center of our star. If the boundary of the solar system shifts by billions of kilometers over a single solar cycle, if the edge of everything we call home is not a fixed address, but a moving surface responding to forces both internal and external, then what does it even mean to say where the solar system ends? The answer, Voyager's data suggests, is that the question itself assumes more stability than actually exists. The boundary is a process, not a location. It is an ongoing physical negotiation between the sun's output and the galaxy's ambient environment, and it has been happening continuously for 4.5 billion years without ever fully settling. And this raises a question that, once asked, does not let go easily. If the solar wind's pressure waves can travel through the heliopause and make interstellar space oscillate, if the sun's eruptions can reach beyond the boundary of the solar system and leave measurable traces in the medium between the stars, then what is traveling in the opposite direction? What is the interstellar medium sending back through that boundary, into the solar system, right now? In 2012, while Voyager 1 was still making its way through the final stretch of the heliosheath, approaching the heliopause, its instruments detected something that had not appeared in any model, any simulation, or any theoretical framework that scientists had seriously entertained up to that point. A region where the magnetic field of the sun and the magnetic field of interstellar space lined up in the same direction. This sounds technical. The implications are not. When two magnetic fields align when they point the same way, rather than opposing each other, charged particles can travel along those field lines freely, without the deflection and scattering that normally keeps them confined to one side of a magnetic boundary. The aligned region acts like a highway, a corridor, a passage through which particles from inside the heliosphere can stream outward and particles from interstellar space can stream inward, moving in both directions simultaneously through the same narrow channel without the boundary doing anything to stop them. NASA scientists called it the magnetic highway. The name is exact. It functions precisely like one. What Voyager recorded inside this region was a simultaneous, dramatic shift in two separate particle populations moving in opposite directions at the same time. Solar wind particles, the low-energy charged particles that the Sun had been continuously producing and flinging outward for the entire 35 years of Voyager's journey, began dropping sharply in count. They were escaping outward through the aligned field lines, leaking out of the heliosphere into interstellar space through this channel. At the same moment, galactic cosmic rays, high-energy particles originating from sources entirely outside the solar system, surged sharply upward in count. They were streaming inward through the same corridor, entering the heliosphere from interstellar space. Two populations, two directions, one doorway, both open at the same time. The boundary that the old models had drawn as a wall, the heliopause as a clean, sealed edge where the solar wind stopped and interstellar space began, was revealed to be something categorically different. Not a wall, not even a particularly effective barrier, a permeable membrane with active channels running through it, allowing material to pass in both directions depending on where the magnetic fields happened to align. The heliopause is not one thing uniformly. It has regions where it holds firm and regions where it opens up, and those regions shift as the underlying magnetic geometry shifts. The comparison that makes this concrete: imagine a national border that everyone in the country believes is a solid concrete wall, monitored and sealed from end to end. Then, satellite imagery reveals that what looks like a wall from a distance is actually a wall in some places, and thousands of unlocked gates in others, and people have been walking through those gates in both directions the entire time, without anyone at the monitoring stations realizing it was happening. The border was never what anyone thought it was. The containment was never complete. That is exactly what the magnetic highway revealed about the heliopause. Now consider what is actually traveling through those gates. Galactic cosmic rays are not benign background radiation. They are high-energy particles, protons, atomic nuclei, electrons accelerated to extreme velocities by some of the most violent events in the galaxy supernova explosions. The shock fronts of stellar remnants, the magnetic environments around neutron stars and black holes. When these particles strike biological tissue, they can ionize molecules directly, breaking chemical bonds, damaging cell membranes, and at sufficient doses, shredding DNA strands in ways that ordinary radiation does not. Astronauts in low Earth orbit are partly shielded by Earth's own magnetic field. Astronauts on the Moon, or in deep space beyond Earth's protection, are exposed to significantly higher cosmic ray fluxes. Beyond the heliopause, outside the partial shielding the heliosphere provides, the galactic cosmic ray environment becomes a serious and unsolved engineering problem for any crewed mission. And those particles are coming in through the magnetic highway right now, not in theory, not as a projected risk for some future mission. Right now, as the Sun goes through its activity cycle, as the magnetic geometry at the heliopause shifts and realigns, galactic cosmic rays are filtering through the boundary and propagating inward through the solar system, reaching the inner planets, interacting with planetary magnetic fields, contributing to the radiation environment that spacecraft and any living thing in deep space must contend with. The magnetic highway also complicated the question of exactly when Voyager 1 crossed the heliopause. Because the particle signatures that scientists used to confirm the crossing, the drop in solar wind particles, and the rise in cosmic rays both began changing while Voyager was still inside the magnetic highway region, before it had definitively crossed into interstellar space. The crossing was not a single sharp moment, but a drawn-out, back-and-forth process as the spacecraft moved through a boundary that was itself dynamic, shifting, and porous. Scientists debated for months about the precise date of crossing because the data did not show a clean line. It showed a negotiation. That messiness is itself information. A perfectly sealed, static boundary would produce a clean, instantaneous crossing signature. What Voyager recorded was gradual, variable, and directionally inconsistent, exactly what you would expect from a boundary riddled with channels and subject to continuous change. The magnetic highway did not just reveal a new physical structure. It revealed that the entire concept of the heliopause as a fixed, definitive edge was an oversimplification that the data could no longer support. The boundary is real. The transition from solar-dominated space to interstellar-dominated space is real. But it is not a wall. It is a coastline, irregular, shifting with the tides, with channels and inlets running through it that no map had ever recorded before Voyager went there and measured them directly. If the boundary can be permeated, if particles cross it freely in both directions through channels that shift and realign with the magnetic geometry, then what exactly is that environment on the other side? And how dangerous is it really? For a long time, interstellar space was imagined as emptiness. Not complete emptiness, physicists understood that the space between stars contains gas and dust, magnetic fields, and energetic particles. But the working picture, the one embedded in models and taught in classrooms, treated the interstellar medium as a relatively thin, relatively uniform background environment, sparse, cold in most regions, magnetically simple compared to the dynamic interior of a stellar system. The kind of environment that, while technically not a perfect vacuum, was close enough to one that it could be modeled with straightforward assumptions and a manageable number of variables. Voyager 1 entered that environment in August 2012, and what its instruments found, transmitted back across 17+ hours of signal travel time, systematically dismantled the simplified picture that physicists had relied on for decades. The first surprise was density. The plasma density in the local interstellar medium, the concentration of charged particles in the space just beyond the heliopause, came in significantly higher than pre-Voyager models had predicted. The instruments measuring plasma waves detected oscillations consistent with a denser medium than the theoretical baseline. This was not an enormous discrepancy in absolute terms, but in the context of models that had been calibrated carefully and considered reliable, it was enough to force a reconsideration. The interstellar medium just outside the solar system is not as thin as the models assumed. It has more material in it, more plasma, more thermal energy. The space between the stars, at least in this local region, is fuller than the textbooks suggested. The second surprise was magnetic, and this one hit harder. Before Voyager crossed the heliopause, the best available data about the direction of the interstellar magnetic field came from indirect measurements, observations of how the heliosphere was shaped, inferences from the behavior of energetic neutral atoms detected by spacecraft like IBEX, and theoretical models of the local interstellar cloud that the solar system is currently moving through. From all of this, scientists had assembled a consensus estimate of the interstellar magnetic field direction where it pointed, how it oriented relative to the solar system's motion, how it interacted with the heliospheric magnetic field at the boundary. Voyager 1's direct measurements disagreed with that estimate by approximately 40 degrees. 40 degrees is not a small discrepancy. In magnetic field geometry, 40 degrees of directional offset is the difference between two entirely different structural configurations. The interstellar magnetic field was not pointing where the models said it should be pointing. It was rotated significantly relative to every estimate that had been derived from indirect measurement. And because so much of the theoretical framework for understanding the shape and behavior of the heliosphere depends on the orientation of the external magnetic field pressing against it, a 40-degree error in that orientation propagated through the models like a crack through glass, calling into question not just one calculation, but the reliability of the entire inferential chain that had been built on top of that assumption. The models had to be rebuilt, not tweaked. Rebuilt. Then there were the cosmic rays, Inside the heliosphere, galactic cosmic rays are partially deflected and scattered by the heliospheric magnetic field, producing a relatively isotropic distribution arriving roughly equally from all directions. The expectation for interstellar space was a similarly diffuse, roughly uniform background of cosmic ray flux, perhaps slightly more intense than inside the heliosphere, but not dramatically different in character. What Voyager's instruments found was more structured than that. The cosmic ray flux in the local interstellar medium was not a featureless background. It had directionality. It had regions of higher intensity and lower intensity. It had a texture, not the smooth, even radiation bath that simplified models predicted, but something with internal structure, flowing and concentrated in ways that reflected the complexity of the magnetic and particle environment the solar system is actually embedded in. The analogy that captures this most honestly, stepping outside the house expecting fresh air and finding instead a complex, structured weather system that nobody had bothered to forecast properly. Not because the meteorologists were careless, but because they had never had an instrument outside the front door before. They had been modeling the weather from inside a sealed room, using sensors mounted on the interior walls, and doing their best. The moment the door opened and a real measurement was taken from the other side, the gap between the model and the reality became impossible to ignore. One physicist, describing the experience of receiving and analyzing the first confirmed interstellar data from Voyager, put it this way: it was like opening the door expecting a clear day based on the forecast and finding a blizzard. Not a slightly different kind of weather, a categorically different situation that the instruments inside had simply not been capable of predicting. The local interstellar medium is hot, not in the sense that temperature means in everyday life, but in the plasma physics sense, where temperature describes particle energies. The interstellar plasma just outside the heliopause carries thermal energy at levels the old models underestimated. It is magnetized in a direction that required revising the theoretical framework used to understand heliospheric structure. It contains cosmic rays distributed in patterns more complex than uniform diffusion. And it is dynamic, not a static backdrop against which the solar system moves, but an environment with its own structure, its own variation, its own response to the solar system's presence moving through it. All of this comes from one spacecraft, measuring one trajectory through one small region of the boundary between one stellar system and the interstellar medium, one data point in a galaxy of 200 to 400 billion stars, each presumably surrounded by its own heliosphere, each embedded in whatever the local interstellar medium looks like in its particular neighborhood. Voyager has given humanity its first ground truth measurement of what interstellar space actually is. And the measurement says more complex, denser, more magnetically structured, and more energetically active than the models assumed. The space between the stars is not empty. It is not simple, and it is not waiting passively for anything to cross it. And if the environment right outside the solar system is already this complex, this structured, this different from every prediction, then where exactly does humanity's dream of interstellar travel actually stand? The nearest star to our sun is Proxima Centauri, sitting at a distance of 4.24 light-years. That number gets stated so routinely in science communication that it has lost its ability to shock. 4.24 light-years. It sounds manageable, a small number, a single digit with 2 decimal places. But strip away the abstraction and look at what it actually means in physical terms, and the number becomes something else entirely. Light travels at approximately 1,080,000,000 kilometers per hour. 4.24 light-years is the distance light covers in 4 years, 2 months, and roughly 3 weeks of continuous travel at that speed. In kilometers, it works out to approximately 40 trillion kilometers. 40 million million, a number so large that the human mind has no honest way to hold it. Voyager 1 is currently moving at approximately 73,000 kilometers per hour. That sounds fast. Relative to anything in ordinary human experience, it is almost incomprehensibly fast, roughly 60 times faster than a rifle bullet, fast enough to circle Earth in under 36 minutes. And at that speed, covering the distance to Proxima Centauri would take approximately 73,000 years, not decades, not centuries. 73,000 years. Agriculture was invented roughly 12,000 years ago. The gap between now and the construction of Stonehenge is about 5,000 years. 73,000 years ago, modern humans were sharing the planet with Neanderthals and had not yet reached Australia. That entire span of time, every civilization, every language, every written word, every war and discovery and work of art that humanity has ever produced represents less than 1/5 of the travel time required to reach our nearest neighboring star at the speed of the fastest object humanity has ever launched. This is the first wall. Distance so vast that it does not yield to incremental engineering improvements. Getting to Proxima Centauri in a human lifetime, or even in the span of a recognizable civilization, requires not better rockets, but a different category of physics. Propulsion concepts capable of achieving a significant fraction of the speed of light, which would require energy outputs that dwarf anything humanity currently produces or has any near-term prospect of producing. The distance problem alone, without any other consideration, makes interstellar travel an undertaking of a completely different order than anything the space age has yet attempted. But Voyager's data added a second wall, and in some ways, it is more immediate than the first. The interstellar medium beyond the heliopause is not a neutral transit corridor. Voyager's measurements confirmed that the local interstellar environment contains galactic cosmic rays, high-energy particles moving at significant fractions of the speed of light at flux levels that the heliosphere partially shields the inner solar system from. Outside the heliopause, that partial shielding disappears. A spacecraft or crew operating in interstellar space would be exposed to the full galactic cosmic ray environment without the protective buffer of the solar wind and heliospheric magnetic field behind them. The consequences for electronics are serious. High-energy cosmic ray particles can penetrate shielding material, strike semiconductor components, and flip binary states in computer memory, a phenomenon called a single event upset. In the low Earth orbit environment, this happens occasionally and is managed through redundant systems and error correction protocols. In the interstellar cosmic ray environment, it would happen far more frequently and with higher energy particles capable of causing more severe damage. Any spacecraft designed for interstellar transit would need radiation hardening far beyond current standards, and the mass cost of adequate shielding, given that shielding effectiveness scales with material density and thickness, represents an engineering challenge that no current or near-future propulsion system could carry over interstellar distances. For a human crew, the situation is starker. The human body has no mechanism to repair the specific kind of DNA damage caused by high-energy heavy ion cosmic rays, the ionization tracks left by fast-moving nuclei of iron, silicon, and other heavy elements accelerated to near-light speed by distant supernovae. Extended exposure to this radiation environment causes cumulative neurological damage, significantly elevated cancer risk, and cellular injury that no amount of pharmaceutical intervention currently known can fully prevent or reverse. The heliosphere and Earth's magnetic field together reduce the galactic cosmic ray flux reaching the surface to a level human biology can tolerate over a lifetime. Remove both of those shields simultaneously, as any interstellar mission necessarily would, and the biology problem becomes as difficult as the propulsion problem. The comparison is precise and uncomfortable. A strong swimmer in a well-maintained pool knows the depth, knows the edges, has lifeguards nearby, and moves through a controlled environment where the risks are bounded and understood. The ocean is different in kind, not just in degree. No bottom you can reach, no wall to grab, currents that move independently of anything you do. Things living in the water that you have never seen and were not trained to handle. The swimmer's skill is real, but the environment has changed so completely that skill alone is no longer the relevant variable. That is the relationship between everything humanity has done in space so far and what interstellar travel actually requires. Low Earth orbit, the Moon, Mars, even the outer planets, all of it sits inside the heliosphere, inside the partial protection of the solar wind and the sun's magnetic field. Interstellar space, as Voyager's data describes it, is categorically different, more energetic, more complex, more hostile to both electronics and biology than any environment humanity has yet operated in. And the transit time, even with propulsion systems far beyond current capability, would likely span decades, at minimum decades, during which a crew would be exposed to this environment continuously, with no possibility of rescue, resupply, or return within any reasonable time frame. There is a version of this conversation that ends with optimism about breakthrough propulsion and advanced shielding and generation ships and all the engineering solutions that science fiction has been proposing for a century. Those conversations are worth having, but they require honesty about the baseline first. And the baseline, as Voyager has now measured it directly, is that the space between stars is not an empty highway waiting for a fast enough vehicle. It is a high radiation, magnetically complex, poorly mapped environment that kills electronics and damages biology, stretching across distances that dwarf every scale of reference humanity has ever used. Voyager did not make interstellar travel impossible. It made the honest accounting of what it actually requires unavoidable. But Voyager did not only show us how far away the stars are, or how hostile the path between them is. It showed us something more fundamental, that the solar system itself is larger, more complex, and more dynamically alive than any model ever dared to imagine. Most people, if asked where the solar system ends, would point to Neptune. It is a reasonable answer. Neptune is the outermost planet, the last major body orbiting the Sun, sitting at an average distance of approximately 30 astronomical units from it. Beyond Neptune, the thinking goes, is empty space, the edge of the family, the end of home. It appears that way on diagrams. It gets taught that way in school, and it feels intuitively correct because Neptune is the last thing on the map with a name and a clear identity. It is also wrong, not partially wrong, wrong by a factor that makes the error almost comic once you see it clearly. The heliopause, the boundary where the sun's influence ends and interstellar space begins. The threshold that Voyager 1 crossed in 2012 sits at approximately 121 astronomical units from the sun. Neptune orbits at 30 astronomical units. That means the actual outer boundary of the solar system, defined by the reach of the sun's own solar wind, extends more than 4 times farther than the orbit of the outermost planet. If you drew the solar system to scale and marked Neptune as the edge, you would need to extend your drawing 4 times further in every direction, just to reach the heliopause. Everything between Neptune and the heliopause, the Kuiper belt, the scattered disk, the vast outer reaches of the heliosphere itself, is still the solar system, still inside, still home. And the heliopause is not even close to the outer limit of the sun's gravitational domain. Beyond the heliopause, extending outward to distances almost impossible to state without pausing to absorb them, lies the Oort cloud. This is a vast, roughly spherical shell of icy bodies, comets, frozen planetesimals, remnants of the solar system's formation, gravitationally bound to the sun, but sitting so far out that they are barely bound at all. The outer edge of the Oort cloud is estimated to reach somewhere between 50,000 and 100,000 astronomical units from the sun. 100,000 astronomical units. In light years, the unit used to measure distances between stars that is approximately 1.6 light years. The nearest star system, Alpha Centauri, is 4.24 light years away. The Oort cloud extends more than a third of the way to the nearest star. The Sun's gravitational influence, the domain over which it holds sway over orbiting bodies, does not end at Neptune. It does not end at the heliopause. It extends to 100,000 astronomical units to within a light year and a half of the next stellar system. The solar system is not a compact planetary family with a clear edge. It is an enormous gravitational territory, most of which is invisible, mostly unmapped, and filled with objects we have never directly observed. Voyager 1 has been flying for nearly 50 years. It crossed the heliopause. It is in interstellar space, by the definition that matters most physically beyond the solar wind, beyond the heliospheric magnetic field, exposed to the full interstellar environment. And yet, by the broader definition of gravitational reach, it has barely left. To exit the Oort cloud, to truly leave the Sun's gravitational domain, Voyager 1 would need approximately 300 more years of travel at its current speed. 300 years from now, in the year 2325, Voyager 1 will finally cross beyond the outermost boundary of what the Sun can claim as its own. The comparison that makes this scale tangible? Imagine you are standing inside a room in a skyscraper at the center of a sprawling city. You step out of the room into the hallway, and someone tells you that you have left the city. You have not left the building. You have not left the floor. You have not left the block. You stepped into a corridor. That is Voyager 1 crossing the heliopause, a genuine and historic threshold, but still inside the larger structure in ways that the tidy planetary diagrams never communicate. 300 years? Think about what that span of time means in human history. 300 years ago was 1725. Isaac Newton had published his laws of motion fewer than 40 years earlier. The United States would not exist for another 50 years. The steam engine had not been invented. Everything that humanity has built, discovered, and transformed since the early 18th century, the Industrial Revolution, electricity, germ theory, relativity, computing, spaceflight, the internet, all of it fits within the time Voyager still needs just to clear the outer edge of the solar system's gravitational reach. And Voyager 1 is already the fastest human-made object ever to leave the solar system. There is no faster option currently flying. There is no mission behind it moving at greater speed. The object representing the outermost reach of human engineering, after nearly 50 years of continuous flight, still needs 3 centuries to exit the solar system completely. The Oort cloud will not be crossed in any human lifetime currently alive, or in the lifetimes of their grandchildren, or their grandchildren's grandchildren. It will be crossed by a spacecraft that launched when Gerald Ford was President of the United States. If the spacecraft holds together long enough, which it almost certainly will not, since power will run out long before 300 years have passed. The solar system, understood fully, is not a small neighborhood with clear edges and a tidy boundary. It is a gravitational empire stretching nearly a light year and a half in every direction, most of it dark, cold, and completely unknown to direct observation. What humanity thinks of as the solar system, the Sun, the 8 planets, the familiar diagrams, is the bright, warm center of something vastly larger that extends far into the space we casually call interstellar. And if the solar system is already this enormous, a structure reaching nearly to the nearest star, then what does it mean to ask where we are inside the Milky Way? What is our actual position in the galaxy, and how significant is it? The solar system is moving? Not just Voyager, not just the planets in their orbits. The entire solar system, the Sun, every planet, every moon, every comet in the Oort cloud. Voyager 1 and Voyager 2, and every other spacecraft humanity has ever launched, is traveling through the Milky Way galaxy at approximately 828,000 kilometers per hour, not relative to something nearby. Relative to the galactic center, around which the entire solar system is orbiting in a vast, sweeping path that takes between 225 million and 250 million years to complete one full revolution. This duration has a name: the cosmic year, sometimes called the galactic year, the last time the solar system was in its current position in the Milky Way. The most complex life on Earth was early dinosaurs. The time before that, the first land vertebrates were only beginning to appear. Every complete orbit of the galaxy represents a span of time so large that it contains the entire history of complex animal life on Earth, start to finish, with room to spare. In the entire recorded history of human civilization, from the first written language in Mesopotamia to this moment, the solar system has completed approximately 0.001% of one galactic orbit. Stretch that to the full span of Homo sapiens as a species, roughly 300,000 years, and the number improves to approximately 0.0085%, not even 1/100th of 1% of one lap. In the time our species has existed, the solar system has moved through the galaxy like the hand of a clock that has barely twitched since it was set. This motion matters for understanding the heliosphere in a way that rarely gets discussed outside technical literature. The solar system is not sitting still inside a uniform interstellar medium. It is plowing through the galaxy at 828,000 kilometers per hour, and the interstellar environment it moves through is not uniform. Different regions of the Milky Way have different gas densities, different magnetic field strengths and orientations, different cosmic ray fluxes, different concentrations of dust and ionized plasma. As the solar system travels through the galaxy over millions and billions of years, the heliosphere, that bubble of solar wind and magnetic field surrounding us, encounters different external conditions in different eras. The external pressure changes. The interstellar magnetic field it is pushing against changes direction. The density of the medium pressing on the heliopause shifts. This means the heliosphere has not always looked the way it looks today. In some galactic environments, the solar system has passed through. The external pressure would have been higher, compressing the heliosphere inward. In others, lower pressure would have allowed it to expand. There may have been eras when the heliopause sat significantly closer to the Sun than it does now, reducing the shielding it provides to the inner planets. There may have been eras when the solar system passed through denser interstellar clouds that stressed the heliosphere in ways we cannot directly study because no instrument existed to record them. The heliosphere, in other words, is a dynamic structure responding not only to the Sun's own activity cycle, but to the galactic neighborhood the solar system is currently traveling through. It is a bubble on a boat, and the boat is moving through waters that change character over timescales of millions of years. A useful image picture: a small boat surrounded by a protective bubble, crossing an ocean whose composition changes from region to region, warm shallows in one area, cold deep water in another, dense saline regions that push harder against the bubble walls, dilute regions where the pressure eases. The bubble adjusts its shape continuously in response, sometimes rounder, sometimes compressed, always responding to whatever the water around it is doing. That is the heliosphere and the solar system, traversing the Milky Way over geological and astronomical timescales. The bubble reshaping itself in response to galactic environments that shift over millions of years. And while all of this is happening, while the solar system drifts through the galaxy at 828,000 kilometers per hour, while the heliosphere negotiates its shape against whatever interstellar environment it currently faces, while galactic cosmic rays filter through the magnetic highway in the heliopause and solar wind shock waves propagate out into interstellar space. Human civilization has been preoccupied with the borders between patches of land on a single small planet, arguing over territories that, on any galactic scale, do not register as a rounding error. The Milky Way contains between 200 billion and 400 billion stars. The solar system is one of them, orbiting the galactic center at a distance of approximately 26,000 light-years, somewhere in a relatively unremarkable arm of the spiral called the Orion Arm, not at the center, not at the edge. Somewhere in the middle of one arm of one galaxy, moving at nearly 1 million kilometers per hour through a neighborhood that changes over timescales, human civilization has not existed long enough to observe. Voyager 1, the fastest and most distant artifact of human engineering, has covered enough distance after nearly 50 years of flight to make it less than 1/6,000th of the way to the nearest star. The galaxy is 100,000 light-years across. But Voyager did not only teach us about the scale of space, it taught us something far more difficult, something about ourselves, about what we are, and about the particular kind of creature that builds a machine, points it at the dark, and keeps listening long after anyone expected a signal to come back. In February 1990, Carl Sagan made a request that NASA did not have to honor. Voyager 1 was 6 billion kilometers from Earth, already deep in the outer solar system. Its planetary mission long finished, its cameras powered down to conserve energy for the instruments that mattered scientifically. There was no operational reason to turn those cameras back on, no data of value to collect, no scientific objective to justify the power expenditure. But Sagan had been pushing for this moment for years, arguing that the image itself, whatever it showed, would be worth something that scientific instruments could not measure, not data, perspective. NASA agreed. The cameras turned, and on February the 14th, 1990, Voyager 1 photographed the solar system from the outside, 60 frames capturing the sun and several planets suspended in the dark. In one of those frames, in a scattered band of light caused by sunlight refracting through the camera optics, there's a tiny point, pale, almost invisible, easily missed if you do not know to look for it. That point is Earth. In the final image, Earth occupies approximately 0.12 pixels, not a disk, not a recognizable sphere. A fraction of a single pixel, a mote of light so faint that the camera's own optical artifacts nearly swallow it. Every mountain range on the planet, every ocean, every city, every person who ever lived, every war ever fought, every piece of music ever composed, every empire that rose and collapsed compressed into a smear of light smaller than the period at the end of this sentence, photographed from a distance of 6 billion kilometers by a machine weighing 722 kilograms that had been flying for 13 years on the power equivalent of a household light bulb. Sagan wrote about the image. What he wrote became one of the most widely quoted passages in the history of science communication, and it earned that status not through rhetorical flourish, but through the honesty of its observation. He described the dot. He noted that every human being who had ever lived had lived and died on that pale blue dot. Every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every corrupt politician, and every saint, all of them. On that dot, every act of heroism and cruelty in human history, every religion, every ideology, every certainty about human importance produced by creatures living on a fraction of a pixel, suspended in a beam of light, in the dark. The photograph is a data point. It is also something that data alone cannot fully account for, a reframing so complete that it does not add information so much as dissolve a certain kind of self-importance that human history tends to accumulate without noticing. The pale blue dot photograph does not tell us anything about planetary science that we did not already know. What it does is make the scale visceral rather than abstract. It transforms a number 6 billion kilometers into a feeling, and the feeling is not comfortable. Think about what produced that image. 722 kilograms of metal, wiring, and scientific instruments, a machine lighter than most mid-size cars assembled by human hands in the 1970s, using technology that has since become antique. Pointed at the dark and sent outward on a trajectory calculated with pencils and early computers. That machine spent 13 years crossing the solar system, surviving radiation environments, gravitational forces, and the perpetual cold of space that hovers just above absolute zero. It arrived at a position 6 billion kilometers from its origin, turned its camera around on the instruction of one scientist who thought the picture mattered, and sent back 60 frames of data across a signal so faint it required a dish antenna the size of a building to receive. And from those 60 frames, one image, one pale dot, one pixel fragment in a sunbeam. The same machine, or rather, the same program. Voyager 1 and its twin Voyager 2 went on to cross the termination shock, traverse the heliosheath, map the magnetic bubble structure that no model had predicted, cross the heliopause, and begin transmitting the first direct measurements of interstellar space ever recorded. All of it, from a spacecraft smaller than a compact car. All of it, transmitted on 22 watts of power. All of it, collected over nearly 50 years by a program that was originally designed to last 4. Consider what that means in terms of return on investment, not financial, but epistemic. The ratio between the physical smallness of the instrument and the scale of what it revealed is almost absurd. A 722 kilogram machine changed humanity's understanding of the outer boundaries of the solar system, the structure of the heliosphere, the nature of interstellar space, and through one photograph taken at the request of one scientist, the emotional reality of Earth's position in the cosmos. The machine is smaller than a car. The shift in understanding it produced is civilizational. That asymmetry is worth holding. A spacecraft that a single large truck could carry, running on power that would not light a standard room, moving through space at a speed a modern passenger jet could not approach, has told us things about where we live that nothing else could have told us because nothing else went there. Voyager did not go to interstellar space because humanity had a comprehensive plan for interstellar exploration. It went because a 4-year mission did not get turned off, and the engineers who kept it running had the patience and the conviction to keep listening across decades and billions of kilometers for signals that took most of a day to arrive. The spacecraft is small. The solar system is enormous. The galaxy is incomprehensibly larger. And the creature that built the spacecraft, living on a fraction of a pixel in a sunbeam, is trying to understand all of it, with instruments no bigger than a car and transmission power no stronger than a refrigerator light. That is the mirror Voyager holds up. Not a comfortable one, but an honest one. Voyager's story is not finished, and what is still coming from it will make everything that came before look like the opening chapter of something much larger. As of 2025, both Voyager 1 and Voyager 2 are still transmitting, not in full capacity. Over the decades, NASA has made a series of deliberate, carefully calculated decisions to power down onboard systems one by one: heaters, redundant instruments, non-essential subsystems, in order to extend the operational lifetime of the science instruments that matter most. The power source for both spacecraft is a radioisotope thermoelectric generator, which converts the heat produced by the natural radioactive decay of plutonium-238 into electricity. When the spacecraft launched in 1977, each generator produced approximately 470 watts. Radioactive decay is relentless and mathematically predictable. The power output drops by roughly 4 watts every year. By 2025, The available power has fallen to somewhere in the range of approximately 230 to 240 watts. Every watt matters. Every instrument kept running comes at the cost of something else turned off. Despite that, both spacecraft are still doing science. Voyager 1 is measuring the plasma, magnetic field, and cosmic ray environment of interstellar space from a position over 24 billion kilometers from the Sun. Voyager 2, which crossed the heliopause in November 2018, 6 years after Voyager 1, is measuring the same environment from a different direction, providing the first ever two-point comparison of the local interstellar medium from separate trajectories. No other instruments in history have operated in interstellar space. These two spacecraft, between them, constitute the entirety of humanity's direct in situ knowledge of what lies beyond the heliopause. Every paper published on the measured properties of the local interstellar medium ultimately traces back to data from these two machines. In 2023, something went wrong with Voyager 1. The spacecraft began transmitting corrupted data from its flight data system, the computer responsible for packaging scientific and engineering data for transmission back to Earth. The telemetry arriving at the Deep Space Network was garbled. Engineers could tell the spacecraft was alive and receiving commands, but the data it was sending back was unreadable. For several months, the team at the Jet Propulsion Laboratory worked through the problem, diagnosing a fault in a computer system nearly 50 years old, across a distance of 24 billion kilometers, with a communication round-trip time of approximately 45 hours. 45 hours for one exchange. Send a diagnostic command. Wait 22.5 hours for it to arrive. Wait for the spacecraft to respond. Wait another 22.5 hours for the response to travel back. One question and one answer takes nearly 2 full days. Debugging a computer under those conditions requires a quality of patience and precision that has no real parallel in ordinary engineering practice. The team eventually identified the problem: a single corrupted chip in the flight data system memory, containing code that was producing the garbled output. The solution was to move the affected code to a different location in the memory, a patch transmitted across 24 billion kilometers of space to a computer built in the 1970s, executed successfully, and confirmed working after a 45-hour wait. The spacecraft resumed normal science operations. The data started flowing again. NASA is not being casual about the timeline remaining. The plutonium power supply will reach a point where it can no longer sustain even the minimum instruments required for science return sometime between 2025 and 2030. The exact date depends on how aggressively the team manages the remaining power budget and which instruments are prioritized as the available wattage continues to decline. When the threshold is crossed, when the power finally drops below what is needed, the instruments will fall silent. The transmitter will go quiet. Voyager 1 will continue moving outward through interstellar space at 73,000 kilometers per hour, as it will for billions of years, but it will do so in complete silence. No more data, no more signal, just motion in the dark, forever. Until that moment, the data keeps arriving, and it keeps producing science. Researchers publish new analyses every year based on Voyager measurements, studies of the plasma wave environment in interstellar space, analyses of the cosmic ray flux at different distances beyond the heliopause, comparisons between what Voyager 1 and Voyager 2 are measuring in their respective directions that reveal the directional structure of the local interstellar medium. The mission that was designed to last 4 years is still generating peer-reviewed scientific output in its 48th year of operation. The data archive it has produced will continue to be analyzed for decades after the spacecraft goes silent. There is something quietly remarkable about the support infrastructure this requires. The Deep Space Network. The system of large dish antennas positioned around the globe that communicates with both Voyager spacecraft has to compete for time with every other active NASA mission. Pointing a 70-meter dish at a source 24 billion kilometers away, tracking a signal of 22 watts across that distance, requires scheduling and coordination that is ongoing and resource-intensive. The engineers who maintain contact with Voyager are, in some cases, working with documentation and institutional knowledge that has been passed down through multiple generations of staff. Because the original designers are no longer available, keeping this mission alive is an act of sustained institutional commitment as much as it is an engineering achievement. NASA can patch a computer from 24 billion kilometers away using a 45-hour round-trip signal, diagnosing a chip fault in a 50-year-old system, and writing corrected code across interstellar distances. Meanwhile, the average laptop repair still requires a trip to the store and a week's wait. The humor is real. So is the achievement. Both things are true simultaneously, and neither diminishes the other. But there is one question that all of this data, every measurement, every corrected transmission, every paper published from Voyager's 50 years of observation has not answered, cannot answer, may never answer. And it is the largest question that everything Voyager found actually raises. Everything Voyager discovered the asymmetric heliosphere, the magnetic foam, the porous boundary riddled with highways, the solar shock waves propagating into interstellar space, the denser than expected plasma, the misaligned magnetic field, the structured cosmic ray environment, all of it came from a single point in interstellar space. One trajectory, one direction, one spacecraft measuring one narrow corridor through the boundary of one stellar system. At one moment in the 4.5 billion-year history of that system's existence. Voyager 2 adds a second trajectory, a second direction, a second set of measurements, and already the two data sets disagree in ways that reveal the local interstellar medium is not uniform even across the relatively small angular separation between the two spacecraft's paths. 2 data points, and they do not match. The environment is more variable than even the post-Voyager revised models had assumed. Now scale that outward. The Milky Way contains between 200 billion and 400 billion stars. Not all of them produce stellar winds strong enough to generate a heliosphere-equivalent structure, but a significant fraction do. Main sequence stars like the Sun, which make up the bulk of the galaxy's stellar population, generate continuous stellar winds that interact with the surrounding interstellar medium in precisely the same way the Sun's solar wind does. They produce their own termination shocks, their own equivalent of the heliosheath, their own astrospheres, the general term for heliosphere-like structures around other stars. Each one is embedded in the same interstellar medium, pressing outward against it, shaped by it, negotiating with it continuously. Each one is almost certainly asymmetric. Each one almost certainly has its own magnetic structure, its own equivalent of the foam-like magnetic bubbles Voyager found in the heliosheath, its own porous boundary where the stellar and interstellar magnetic fields align and particles flow through in both directions. Each one pulses with its host star's activity cycle. Each one is shaped by the particular region of interstellar medium it happens to be moving through at this moment in galactic time. And all of those astrospheres, 200 billion of them. 400 billion of them exist in the same galaxy, separated by distances measured in light years. All of them embedded in the same interstellar medium. All of them interacting with it simultaneously. The question Voyager actually leaves behind is not about the edge of the solar system. That question has been answered, imperfectly, but genuinely, by the data the spacecraft has transmitted over nearly 50 years. The question Voyager raises, the one that follows logically and inescapably from everything it found, is about the interstellar medium itself. If the boundary of our solar system is this complex, this dynamic, this different from what any model predicted, and if every other stellar system in the galaxy has its own equivalent boundary doing the same thing, then what is the interstellar medium that all of these systems are simultaneously pushing against and being shaped by? The interstellar medium is not a passive background. Voyager proved that. It has structure, it has magnetic orientation, it has pressure gradients and density variations and cosmic ray distributions that are neither uniform nor random, but organized in patterns that reflect processes operating at galactic scales, supernova remnants, stellar winds from millions of stars interacting over millions of years, the large-scale magnetic structure of the galaxy's spiral arms, the motion of everything through everything else at velocities measured in hundreds of kilometers per second. What Voyager measured at the heliopause is a single point of contact between one stellar system and that galactic scale environment. And that single point of contact was already more complex than the best models in the field had managed to describe. The entire framework of understanding, built over decades, refined with care, supported by indirect evidence from multiple sources, failed to predict what a direct measurement would find. That failure is not a criticism of the scientists who built those models. It is a statement about the difficulty of the problem. The interstellar medium is shaped by processes happening across the entire galaxy, over timescales longer than Earth has existed, modeling it from inside one stellar system, using instruments that had never left that system, was always going to produce an approximation. The approximation was the best available, and the best available was still significantly wrong. Voyager did not show us the edge of the solar system. That is what the mission is often described as having done, and it is not inaccurate, but it is incomplete. What Voyager actually showed us is that we do not yet know what we are living inside. The heliosphere is not a boundary in the sense of a wall or a border or a defined limit. It is a thin, dynamic, permeable layer, a membrane, not a shell separating the solar system's interior environment from a galactic environment that dwarfs it in every dimension. It is the outermost layer of something that has not yet been fully described. A structure embedded in a larger structure, embedded in a larger structure still, each layer more complex than the one inside it, each one currently beyond the reach of any instrument humanity has yet deployed. The heliosphere is not our border. It is our skin. And like skin, it is permeable, responsive, and far thinner relative to what it contains than it appears from the inside. Sometime between 2025 and 2030, the power will run out. The transmitter will fall silent. Voyager 1 will continue moving through interstellar space through the local interstellar cloud, eventually into whatever lies beyond it, outward into the galaxy at 73,000 kilometers per hour, in complete silence, for longer than the Earth has existed. Billions of years from now, the Sun will have expanded into a red giant and incinerated the inner solar system. The Milky Way will have merged with the Andromeda Galaxy. The stellar neighborhood will be unrecognizable, and Voyager 1 will still be moving, somewhere in the resulting galaxy, carrying no power, transmitting nothing, remembered by no one, except for one thing. Bolted to the body of each Voyager spacecraft is a golden record, a 12-inch gold-plated copper disc, encased in an aluminum cover, carrying 115 images of Earth, greetings in 55 languages, sounds from the natural world, rain, wind, surf, the calls of birds and whales, and 90 minutes of music from across human cultures. The cover includes instructions for playing the record, encoded in a form that assumes only knowledge of physics and the hydrogen atom, because those are the only things that can be assumed to be universal. The record was not included for scientific purposes. It carries no data about the heliosphere or planetary atmospheres or solar wind particle counts. It was included because the people who designed this mission understood, at some level, that they were sending something out that might outlast everything else humanity would ever build. The spacecraft will travel for billions of years. The record is designed to survive that journey. And somewhere encoded in the reasoning of the people who put it there was an acknowledgement that the universe is large enough and old enough and possibly populated enough that the record might someday be found. The only thing humanity has ever sent into interstellar space with the explicit hope that someone else might find it is not a weapon, not a territorial marker, not a claim of dominance. It is evidence. Evidence that on a pale blue dot orbiting an unremarkable star in an outer arm of a mid-sized galaxy, something became conscious, looked outward, wondered what was there, built the best machine it could with the knowledge it had, pointed it at the dark, and kept listening for nearly 50 years to a signal weaker than a refrigerator light, coming from the edge of everything it had ever called home. That signal is still coming, for now.